All right, so that's pretty much it.
I'm not sure about this stuff should be the double year insulin than I'm not sure because it's not. I mean, if you look at the data, it doesn't seem to be all one that. Curious why some insulin than anemic and top. Should get to pump. Did you look the student?
No, I'm okay.
Okay.
All right.
Okay.
I can't see the menu bar. Oh yeah, I see it. Let's see Google Chrome. This one's Google Chrome, right? Close. Yeah, you're good to go. Thank you.
Good afternoon, everyone. My topic today is oceanic response to mesoscale LC coupling. So before I go to the result, I want to briefly introduce some basic mechanism for the mesoscale LC coupling. So this one shows the important influence of the mesoscale LC coupling on the eddy kinetic energy. Suppose we have anticyclonic eddy. So to the north, the eddy current will go to the eastward, and to the south, then on the south side will go to the westward. And we know the wind stress is not simply dependent on the wind speed itself, but depends on the difference between the wind speed and the ocean current. So on the north side, the wind and the ocean current go in the same direction. So the wind stress is somewhat smaller. But on the south side, because the wind and the ocean current go to the opposite direction, so the wind stress is stronger. We know on the south side, the wind going to the same direction, they do positive wind work. On the south side, they do negative wind work. But the magnitude of negative wind work is always larger than the magnitude of the positive wind work, because the wind stress on the south side is larger than that on the north side. So if we average the wind work over the entire eddy region, we see a negative wind work. At the mesoscale, because the influence of ocean current on the wind stress, the atmosphere always do negative wind work on the mesoscale eddies. This provides a dissipation mechanism for the eddy energy.
Shouldn't it be for any eddies or just mesoscale eddies? Like if I had a bigger eddy also, it would.
Yeah, I think because you have smaller eddies, the current associated with the eddy is very, very weak. Okay. So the influence of the current on the wind stress is negligible. But for the mesoscale eddies, current is very strong.
Okay.
So another important influence which only be well realized in recent years is the influence of eddy on the heat flux. So this figure shows the composite analysis of the eddy-induced heat flux. This shows the heat flux in the anticyclonic eddies minus the values in the cyclonic eddies. Which you can see that in the anticyclonic eddies, because there is a warm temperature normally, the turbulent heat flux into the atmosphere is enhanced. The opposite is true in the cyclonic eddies. So we see a positive relationship between the mesoscale SST and the turbulent heat flux into the atmosphere. Because the turbulent heat flux into the ocean have a negative sign, this means the turbulent heat flux into the ocean is negatively correlated to the SST. So the turbulent heat flux into the ocean the product of turbulent heat flowing into the ocean and the mesoscale SST is a negative value. This means that the eddy-induced turbulent heat flux always try to decrease the eddy temperature, so the temperature variance itself. This further reduces the eddy potential energy. But how important this mechanism is on the ocean energy budget is remain unclear. So we try to understand how this mechanism important or not important. So we do a experiment.
So the coupling in the standard case, both the kinetic energy and potential energy is actually damped.
Yeah.
Destroyed by the RC coupling.
Yes. But the former, this one is well understood. But this one remains unclear.
Right, but on the other hand, well, I guess you're going to get to that. That picture you showed earlier, that's not really considering the RC coupling, right?
This one.
Right. So there's no response. The background wind you assume to be unaffected by the SST.
Yeah. But if affected by the ocean current.
Affected by the ocean current. But in real system, the wind itself also depends on eddy.
Yeah, yes.
Right. So the strength of the winds is actually modified instead of a constant. Actually, also has a structure.
Yeah, I agree.
Right.
Yes. So there are also a thermal effect on the wind.
Right, and that thing is also not understood at the moment.
No, it hasn't been understood.
Actually, no, there's no paper on that at all. No studies on that at all.
And you might address it later in your talk, but this just says that it's going to be negative, but do you know how big it's going to be? People don't really know. Is it a big chunk or a small chunk?
I have read some papers. In some papers, they say if we remove this effect, the eddy can become 20 or 30% stronger. The eddy kinetic energy.
So it's a significant.
Yeah.
damping.
In fact, we should make a calculation in our model. It's very easy to do to calculate to disable the
the
reference. Just to make the current goes to zero, right? I mean, calculate the stress. So it'd be really interesting to compute the kinetic energy, how much increase it is.
Yeah.
But there's a subtlety to the change in the wind too. That actually changed the wind work.
Yeah.
And that part is not understood at all.
No.
Yeah, the whole thing, including the surface current, is a little bit, because you include the wind current where? In the stress computation?
Yes.
Or is this allowed to go all the way up through the layer, through the boundary layer or not? It's kind of weird.
I don't think you can.
Yeah.
Well, you can adjust it to the lower level to take into account that.
Well, I mean, theoretically speaking, the stress and momentum flux is really done by the turbulence mixing. So what we really need to do is actually have a wave model coupled to this, and that's really the right way to do it.
But even beyond that, if something is moving, the interface is moving, right? So instead of going to zero, where the interface is supposed to be static, it goes to zero, where by taking into account the fact that it's moving.
That's the law of the war. You have to do that.
So the whole profile changes.
No, the whole profile only depends on the value needed at the surface stress.
Right.
Because the logarithm profile is determined, there's only one value near the surface to determine the thing.
But I don't think this is
I don't think you're allowed to change the law of war profile, because that's an empirical formulation.
But where the boundary conditions are. It has to be zero here.
Right.
It's zero because it's also moving. So it's if you.
But I don't think you can easily adjusting the value of the stress value in the interior.
That's what I'm saying. So it's not correctly really implemented the way it is right now. Because
Basically, you're saying that the atmosphere feel it too.
Yeah.
Yeah, it has to feel it, but it's really not.
It does feel it because it feels the value, the log of the water profile is going to change when you adjust to the lower value.
But people run atmospheric models, uncoupled models around without this effect anyway.
Right.
You don't need the current, you only need SST.
Right.
So I guess the assumption is in the atmosphere it's not important.
Yeah, probably not.
We don't know, but it's an assumption.
Okay, sorry.
So this experiment had been repeatedly introduced by Xiaohui and Xue. So I just want to give a brief introduction. So because we have a high resolution couple regional climate model. The atmosphere model is by WRF with 9 kilometer resolutions, and the ocean model is ROCS and also 9 kilometer resolutions. So at each coupling time step, the ocean transfer the ocean current transfer ocean current and ST formation into the atmosphere. And the atmosphere using this information to calculate the wind stress, heat flux, freshwater flux, and transfer this computed flux into the ocean to force the ocean. So in the control round, they are regularly coupled, so all the information of the ocean current and the SST is transferred into the atmosphere model. But in the filter round, we still transfer all the ocean current information to the atmosphere model, but we only before we transfer the SST, we apply the lowest filter to remove the mesoscale SST. So only the large scale SST is transferred into the atmosphere model. So basically, this mechanism is not included in the filter round.
So, but this one includes the wind stress.
Yeah,
part,
it's
all the
the-
time.
yeah.
Always.
So the comparison between the control round and filter round give an opportunity to evaluate how important this heat flux effect on the ocean ocean energy budget. So for each simulated round, we have 5 ensemble. So far, we have 5 ensemble members. Each ensemble member starts from a different year, but both from the October 1st and the round is run for half years. So only the winter term is covered. This figure shows the standard derivation as STST in the control round, and this one shows the filter round, and this one shows the difference. So after we remove this mesoscale LC some thermal coupling effect, the temperature variances become much stronger in the filter round. So we can so do a further analysis. We choose this box region and define the mean flow as the zonal mean field, and the eddy field as a perturbation from the zonal mean.
So this standard deviation is for the high pass filtered SST, right?
So
The large scale has been removed.
No,
That's the total.
it's just remove the signal 5.
Okay.
But why would the filter have a higher variability?
That's the
So
top.
that's the top. That's the.
That's the punchline.
so because we, I mean,
You can tell him later.
so we using this mean field zonal mean as a mean field and the perturbation from zonal mean as a eddy field. This is only a very rough definition to define eddies. So this figure shows the evolution of the horizontal wave number spectral with time for the surface eddy temperature variance. So this is a control round and this is filter round. This is 1,000 kilometers. This is 100 kilometers. So this is the difference. We can see that in the filter round, after we remove this thermal damping effect, the temperature variance in the mesoscales from 100 kilometers to 1,000 kilometers become very strong, become much stronger.
What is the y-axis?
Sorry?
Y-axis the days.
Days,
Okay.
yeah, for 100,
It's a
180
evolution
days.
of this.
Yeah. Yeah, we can see this effect emerge very quickly. Only after 2 or 3 days, we can see a very significant difference.
And the maximum occurs at what, about 500 kilometers? So
Yeah, 300 kilometers.
300
Okay,
kilometers.
this is a logarithm scale.
Okay.
So is the negative also significant, or is
I'm not sure.
And this is 5-member ensemble mean, right?
Yeah,
So you could do a statistical test, I guess.
so can you decrease 1,000 kilometers?
Right.
Yeah.
1,000 kilometers is that it's not eddies, right?
And not
It's-
eddies,
okay.
yeah.
It's probably recirculation gyre scale or something like that.
but basically in the mesoscale, we can see an increase.
What does that mean? So it's like, so you have blue till 100 days and then it's
Yeah,
up. What does that mean? That the variance is increasing?
yes. Yes, actually the,
You go the other way.
Is it because seasonality or just spin up?
I'm not quite sure. Maybe a seasonality.
Seasonal cycle.
Sorry.
Why is eddy variance picking up after 6 months, 3 months?
Temperature variance.
Temperature variance.
Yeah, eddy temperature variance. I think it's probably the seasonality.
Well, the run was spun up already, wasn't it?
No, this run starts from, the run, we spun up the ocean for 5 years, and then we started coupling.
So they must be not, it's just seasonal.
So, well, the couple mode was
So-
really not, it maybe requires some adjustment. Let's do
It's possible, but I think it's probably because we started from October 1st.
Okay.
So the winter seasons, you're getting the stronger currents and
Yes,
you're normally getting a stronger temperature variance.
So look at the control run, and check that.
Yeah.
Spin up run.
Which is the control? That's
No, I mean, if you look at the spin up run, you should check it with seasonality.
Right. Yeah.
100 days is almost to January, so it's already winter.
Yeah.
Right, it is. So you can see the things getting stronger.
Well, ocean winter starts a little
The
later.
transition is kind of sudden, like.
Sorry?
The transition is kind of sudden, I guess.
Well, that's the color effects, I
I think
think.
that's,
I don't think that's that's always the problem with color. You're getting this impression that the things changes very abruptly.
I think the ocean temperature variance responds very quickly to the thermal damping. Only after 10 or 3, less than 10 days, a significant difference had already occurred. So this figure is show the horizontal Wiener spectrum of surface eddy kinetic energy. You can see most of the eddy energy located in the 300 or 400 kilometers.
okay, can you explain this? Or-
I remember Shannon said that for the wave number, this is because the wave number is about corresponds to six times the deformation radius. So if we transfer to the eddy radius, this means about 50 or 60 kilometers. It corresponds to the radius deformation radius of the first biplane mode.
So, I mean, my point was between the control and the filter, there's less difference this time. Actually, the filter seems to be more intense. Can you easily give a reason for that?
Well, that's the thing we're trying to figure out.
Okay.
It's not-
Filter is more intense, that's the point of the talk.
That's the point of the talk.
Yeah,
The reason is because the filter case, you actually remove the damping effect by the atmosphere. Remember that?
Yes, but it
So-
seems
so the
interestingly
eddy-
localized.
So
I
the
mean, and
eddy
that's-
so the eddy gets more intensified.
So, but you just said 60 kilometers. So the filter that you apply is what is the region?
It's the standard
Standard.
filter. It's a
Standard.
15 by 5
15
degrees.
degree.
Yeah.
So it's way larger than that.
So we can also still see a slight increase of the mesoscale eddy kinetic energy in the filter run, but the difference is not significant as the temperature variance. This is the entropy. Because there is a significant increase of the entropy in the filter run from the mesoscale to smaller scales.
The smaller scale is more prominent.
More
Because
robust.
you can see the difference is almost uniform.
But that's just a property of entropy, right? It just
Right.
pushes things to small scale.
Right, but the question is why does when you filter you actually, so we actually had a lot of discussion. So one possibility is that because you remove the atmosphere damping effects, the eddy
Yeah, I
has to
think
dissipate.
first you get the temperature signal, everything
Right.
else follows
Right.
from the temperature.
Right.
So geostrophic to be
Right,
geostrophic.
so it's the eddy has to be cascading to the smaller scale to dissipate. So you enhance the entropy in the system, which is actually really fascinating, actually.
Yeah, very quickly. Less than 20 days. Or
Yeah.
the difference already very significant.
There are some blues also.
Yeah.
it's ultimate.
Those are the mesoscales.
Yeah.
Oh, yeah.
Also, it's
Those are the
transparent.
mesoscales. So the on the right side is actually the small scale. So the eddy are normally cascading when they dissipate, it has to go into the small scale first in order to dissipate.
That's why we see increase there.
So before I show the result below, I want to first introduce available potential energy. So suppose that we have a time stratification which have no horizontal variation. It does have potential energy, but has no any available potential energy that can be transferred to the kinetic energy. So this introduces a concept of available potential energy. So first, we decompose temperature into a reference profile with no horizontal variations and anomaly. So this anomaly will cause available potential energy defined as this formula. Then we can further decompose available potential energy into the mean associated with the mean flow and the eddies. This introduce mean flow potential energy and eddy potential energy. This term, if we sum this term, we will get the total available potential energies.
So mean flow is just time mean, or you're doing spatial vector too?
Zonal mean. So we can have no x derivative.
Okay.
So this is zonally averaged eddy kinetic energy in the control round. This zonal average is between 145 degrees east to 160 degrees east. So this is control round filter round. So for the kinetic energy, we do not see a significant difference between the control round and filter round. So from this difference plot, we can see no significant change of the eddy kinetic energy.
But do you see it at 40 knot?
Yeah, in the 40 knot, we see an increase.
I guess what you mean is that in the area average sense, you don't see.
Yeah, but in this region, yeah, we indeed see an increase. And also, this is also the region with strong temperature variance difference. Yeah, this is also the region with strong air-sea thermal interactions.
Right.
Because typically the air-sea coupling is stronger in the to the north of the front.
Yeah, that's also very curious. I don't understand why.
Yeah. This is for the eddy potential energy. Basically, most of the eddy potential energy is located on the sea surface. This is because the n square is much smaller on the sea surface. Another peak occurs in the frontal region. Generally, because this color bar is actually saturated. So you can see that near the surface region, there is strong increase, very evident increase of the eddy potential energy in the filter round. So
are they the same units? So,
no, actually the eddy potential energy is much larger than eddy kinetic energy.
the same units, different
Yeah,
prices. So
same units. Yeah, the unit here is 12 millimeter
Meter cube.
Yeah.
So the increase is about 20%.
Yeah.
And it's 10 times bigger than the kinetic energy.
Right.
So when you do this eddy potential energy, you just showed us how you compute it. But that means you have to identify the eddies, or it's just computed?
No, you compute it.
So it's on the floor.
It's a
There's no
deviation
tracking.
from,
It's a
these are different
deviation
eddies.
from the mean,
Yeah.
from the zonal mean.
These are different eddies. the
So there
same
might
unit.
be, of course, we assume it belongs to the eddy.
Well, that's the matter of definition. You have to define some kind of,
Right,
what we're
right.
saying is that anything departure from the zonal mean is defined
It's
as
the
eddy.
That's my, yeah.
So that would include the meandering
Yeah,
and things
right.
like that, yeah. But there's no perfect way to do it.
No, but I just wanted
That's
to
always the
understand.
tricky
But this
part.
is a Eulerian diagnostic.
Right.
where
Yeah.
Some of the others are Lagrangian.
The Lagrangian, but Lagrangian is very difficult to do the budget.
Right,
That's the
right.
problem.
Yeah,
You can't do the budget.
Rescale.
What did you explain at the center one? What that segment is?
Yeah. Sorry. So far, I do not have an
It's a
explanation for
front,
this.
it's a front.
Yeah. So basically,
It's front.
it's in the near the front.
So does that mean the stratification is higher at that depth?
No, actually, give this is
Denominator.
normalized by the stratification. So basically, you have weaker stratification, typically you will have a stronger eddy potential energy.
So like a thick isopycal layer.
But this is the 80 potential energy, right?
Mhm.
Is this can we consider this is the region where the conversion really takes place for the paraclinic eddies, the eddy flows?
Yeah, also possible. Because this
So you actually draws a lot of
mean flow potential energy
mean
to
flow
eddy
into the eddy
potential.
kinetic energy. Maybe that explains why
Mm.
there's a secondary maximum. There's a maximum near that depth.
Actually, in this region, the eddy potential energy is even stronger in the control.
Right. I mean, in atmosphere, I'm not sure what's the atmosphere. You probably know this. Right? What is the potential energy eddy atmosphere channel eddy potential energy distribution vertical in the swarm tracks? The kinetic energy definitely is an upper level.
Usually all these temperature things are low levels.
Um,
All
yeah,
temperatures.
yeah. The one peak is the very low level. The other peak is I think the mid troposphere.
So there's two peaks too.
Yeah, but depends on the definition because
Well, in atmosphere, definitely not the use of the zonal mean, right?
yeah. So my definition is so mean, but maybe time
Oh, the time mean.
So
Okay.
yeah, I actually have not been checking the definition.
Okay.
So the eddy heat flux dropped exponentially with height.
Right.
So I think,
Right.
the kinetic energy is not the focus.
Well, the kinetic energy definitely is an upper
But as well
track.
as the density effect.
That's right. That's right.
So,
Mhm.
do you want to look at any other fields like, temperature or density or, velocity, just like this, zonally average?
Yeah, I have a temperature and
Oh,
velocity. Yeah.
But that's in a different scale, right? It's not corresponding to the scale. I mean, if you have the temperature or density distribution zonally averaged, just, if you plot it like that, do you see any correspondence between any of the features in that figure?
I think that would be the next figure, right?
It's for the eddy. If we do a average for temperature, basically we will get a mean flow pattern.
I think he's asking for the next plot though.
Yeah.
This is plotted in the same region, right?
Yeah.
The x-axis is different.
Axis is different, no, axis,
Yeah,
that's the distance. Well, you can explain.
Because this is in this plot we use the axis is fixed on the front itself. So this 0 point is always fixed on the front.
Because we have 5 different ensemble members, right?
Yeah.
In each ensemble member, the main jet of the crucial actually displays in a different location.
Uh-huh.
So we align this temperature plot, always follow the jet core.
Okay.
So plotting here is the distance, so it's a 10 degree away from the jet core in latitudes.
So for the previous
Yeah,
board,
that's-
how do you do that? You don't have to.
So for future we just use the conventional latitude system.
So
We do not
it's
use
also about 10, a little more than 10.
Yeah.
It's a little 12 degrees or something. So it's comparable.
Yeah.
It's a little deeper too.
So this is from one ensemble member or all ensemble members?
This is all ensemble members.
Yeah.
So for this one, you don't have to account for that.
Yeah, for this one, do not do axis.
You can't, it's difficult to do the analysis if you move things.
But for the eddies, we focus on the total energy. But for the front, we have to do using this axis. For otherwise, we will smooth out the front. So this is a zonal mean temperature. So in the control round, filter round, this will look similar. But if we make a difference, we can see that the front tends to be stronger in the control round than the filter round. Because in the filter round, we have a total anomaly to the south of the front, and then positive anomaly to the south of the front. So the temperature gradient actually is weaker in the filter round than the control round.
Is it true? Can you say that for each ensemble member?
So
This is ensemble average, right? You move it, but it's ensemble.
yeah, on average.
But you could do that for each ensemble member and see if it's.
Yeah, for one ensemble member, we do not see this figure. So this probably some noise.
But I don't think we see any decrease either. In one ensemble, we don't see much change.
Neutral.
It's neutral.
Yeah.
In the other 4, you basically see increase.
So there's some variability.
There's some variability.
So because the front becomes stronger in the control run due to the thermal wind relation, we expect a stronger geostrophic zonal mean geostrophic velocity. So actually, it is indeed the case. In the control run, the zonal mean velocity is stronger. So basically, the conclusion here is in the control run, we have a stronger mean flow and stronger front. So to understand why we have a stronger eddy potential energy in the filter run, but a stronger front and mean flow in the control run, we have to do an energetic analysis. Basically, the ocean is a force dissipative system. The forcing typically occurs on the large scale, so occurs on the mean flow. We have wind-driven circulation. It input energy into the ocean. But the dissipation typically occurs on the smaller scales, either through the horizontal dissipation or the vertical mixing. Yeah. So maintain an equilibrium system, the energy must transfer from the mean flow to eddies, either through the barotropical instability or baroclinic instability. And in some regions, the eddy can also drive the mean flow, but this may be not important in the region we consider here, because in the critical extension region, this is the region for the generation of the eddies. Basically, the barotropical and baroclinic instability dominates. So we first construct eddy potential energy budgets. So because we have an acceleration term and an advection term, and also a baroclinic instability term. And this one is a conversion from the eddy potential energy to eddy kinetic energy. And this one is vertical dissipation through the thermal damping mechanism we mentioned before. And we expect in the control run, this one will be large, and in the filter run, because we removed this thermal damping effect, this term should be much smaller. So this is the energy budget. The value shown here is horizontally averaged in the box, but vertically integrated. So the unit is a milliwatt per meter square. So in the upper thermal climb, also include the mixed layer, we see that in the control run, the most important dissipation mechanism for eddy potential energy is actually through the Earth's vertical mixing. That means the LC thermal damping mechanism. And in the filter run, because we remove this mechanism, this term become much smaller.
But you haven't explicitly separated the surface damping versus interior, right? We could
do that.
Yeah, but we haven't done that.
Yeah, but from this difference, we can see most of the difference.
Most likely sort of the
surface.
So this is based on difference. It's a residual.
The last
No,
one
no,
is
no,
the
no.
residual.
No.
The last one.
Actually, it's totally exactly balanced because we computed from the diagnostic file. So this is not residual. But
So for each one, the control, meaning that all the terms balance together. Then the second line is the filter. And the third line is the difference.
How do you compute DPD?
because the model will, in the diagnostic output, the model will output the vertical mixing term.
So it's explicit.
Yeah, split.
Okay, okay.
And
So
everything's done explicitly.
So there is no residual.
No,
There's no residual. It balances out perfectly. Because we write down every term in the temperature equation. Now, talking to Frank Bryan, there's a problem that we write out the daily averages, but he thinks that within 1 day there's also so he's actually writing all the stuff for every time stamp.
Well, it's actually
He accumulates this every term on the fly, and then he actually calculates each term. So he's doing that in top, yeah. So actually, yesterday we had a lot of discussion. So he said he actually increased the output by a factor of 5.
Yeah, but it's phenomenal.
Wow, if you write down all the times in all time steps.
I know.
Accumulated, not every time.
Right. He accumulated this.
But I just went all also that they accumulate quadratic quantities. points.
Right,
To avoid the.
right.
So actually the ROM's average points is in the same way. Easy.
Well, but that's wrong, actually outputs the energetic terms.
Yeah, the diagnosis is also handled the same way. Because
So now we should take a look whether the ROMs actually write out the energy, the kinetic and the potential energy terms. Because
So
we
basically-
actually have to do that ourselves.
So basically, it has two ways of writing it out. One is history files. That's the one over I've seen at one particular time step twice as it is.
Right.
The second is average file, and you define a period for average.
Right.
So it starts accumulating those values
Yeah.
to a single array.
Yeah.
For each time step belong to that period.
Okay.
So once that period is done, then it sums everything together and divides by the number.
Okay.
So that's been automatically
Right.
by ROMs. That's why you get perfect match for the diagnosis times in the temperature balance and moment balance. Otherwise, you won't get the perfect match.
Right.
It is not in that in that sense.
Could you just explain why in the filter run that term is gone?
Because in the filter run, we
Filtered out
the Q prime actually have been surface have been removed.
So there's no correlation between the mesoscale SSD and heat flux.
okay.
Because the atmosphere doesn't see the eddy when we filter.
It's a large scale.
So only sees the large scale, doesn't see the eddy anymore.
Okay.
So this term essentially near the surface just becomes very small.
So another question. You do this daily.
Yeah.
Right?
Yeah.
So the anomaly that you compute is based on the daily,
Yeah.
or you average this
Yeah, also
to be a daily.
Yes, on the daily mean. Everything here. The average value is daily mean. And the,
So basically Q is daily.
Yeah, daily.
Already
Yeah.
average.
Yeah.
So, okay. So that's, yeah,
so in the control run, because we have this in very important discipline mechanism. So in the control run, we have to find an important energy source to balance this important dissipation. So in the control run, we can see that the energy conversion from the potential energy to kinetic energy becomes somewhat weaker. But this difference cannot compensate this huge difference for the vertical dissipation term. So actually, in the control run, the enhanced vertical dissipation is actually balanced by the advection plus the canonical conversion term. Unfortunately, we cannot separate these two terms. So
We can, I mean, we can estimate that, right? I mean, you can try to estimate an advection.
I trust that the error is too large.
Really?
Yeah. The value is actually smaller than the error itself. So this means that for one possibility that the enhanced dissipation of eddy potential energy is compensated by the enhanced advection or enhanced energy transfer from the mean potential energy to eddy potential energies. Both can be possible here.
Well, but if you're considering the rotational components
Yeah.
argument, then this term should be really the baroclinic conversion.
Yeah.
So, which essentially saying that in the control simulation, the energy the eddy gets from the mean flow mostly actually is dissipated by the atmosphere.
Yes.
Right.
Yeah.
Because you can see only, unit 6 or maybe 7 goes to the eddy kinetic energy.
Yeah.
And unit 20 units
Yeah.
actually goes to.
So if we believe this difference comes from the baroclinic conversion, this means that in the filter run, because we remove this dissipation, the ocean eddy does not need to work so hard to absorb energy from the mean potential energy. So this term is reduced. So in the deeper oceans, we do not think very significant difference become the control run and the filter run. So most of the difference actually in the upper ocean.
But if you look at the deeper case, right? I mean, you can see that this term is much smaller.
Yeah.
So assuming those terms are both in the deep ocean, I'm assuming most of this is just due to the advection.
Yeah.
Right.
Yes.
So you can see that the advective effect maybe looks like much smaller because in the deep ocean, the currents in the range between 250 and still is quite strong.
Yeah, but the eddy potential energy is surface intensified.
Right.
Yeah.
Right.
basically you have less variability, that's what you're saying.
Right, well, there's no baroclinic instability generated. There's no
Yeah.
conversion in the deep ocean. Most of the energy conversion occurs in the upper ocean.
So this is something like the Jan McWilliams should calculate this number.
Right. It should, but except that we don't use the GenMac.
No, but if you did use the formula.
You
for
use the
front,
formula, yeah,
to maybe
Right.
try to estimate.
but they don't do explicit calculation of any. And they're assuming any energy is already being generated, and then they rotate the things in a way that,
But you
It will
get a
all-
diffusivity.
right, to get a diffusivity.
So that should be.
That should
greater
be,
For the control.
that's right.
The-
That's right. that's right.
The main point here is that the LC coupling is a dominant mechanism for the dissipation of any potential energies. If we remove this term, this energy budget will change very significantly. So this is the energy budget for the mean flow. We still have the advection term, this baryon conversion term have a negative sign. Actually, this term also occurs in the added potential energy, but have a negative sign. This is a conversion from the mean potential energy to mean kinetic energy, and this is also the work dissipation. But for the mean potential energy.
So you have to compute n squared and divide by that for this term.
Yeah.
It's very noisy stuff.
Yeah, so very noisy. So for the mean flow, we can see that there are also a very significant change of the vertical dissipation. Actually, in the control run, the large-scale heat flux tries to construct the mean front. But in the filter run, the large-scale heat flux tries to destroy the mean front. The reason remains unclear here.
That's really strange.
So this is like you're looking at the front, the Grotius front.
But it looks like if you just look at individual runs, like the control, the thermal damping is actually plays a much smaller role.
Yeah.
Because there's only 2.4
Yeah.
kilowatts per meter square, right?
So the mean flow potential energy, that action plus the BC term actually contribute to.
Well, the mean flow, there's also a forcing term, right? There's seasonal forcing term because I think the heat flux is also included in the potential energy, right?
Sorry, a heat flux?
No, the seasonal forcing of the heat flux
Yeah.
is also, that could explain why the acceleration term is so strong. Because it's simply forced by the external forcing.
Seems that the mean from for our integrating the time span, the mean from become progressively weaker and weaker. So we
Right.
have negative acceleration.
Right.
So for both the mean flow potential energy and the eddy potential energy, we have a difficulty to separate the advection term and the baroclinic conversion term. So to get rid of this problem, maybe you can do a total energy budget. So the available potential energy budget. Here, the BC term vanished because we have summed the eddy potential energy with the mean flow potential energy. There's still a KC term and a vertical dissipation term. But note that the vertical dissipation term mainly comes from the eddies because it's almost much larger than the eddy dissipation for the mean potential energy. So we get a available potential energy budget. And today the control around the vertical dissipation is significantly enhanced. This mainly comes from the eddy dissipation. And it's largely balanced by the advection. This is the true advection, does not have any baroclinic conversion effect included. So because we get an equilibrium state, in the control run, we have a stronger potential energy dissipation. It compensated by the stronger advection. This requires that the mean flow to be stronger in the control run.
Right.
Otherwise, we cannot get a stronger advection.
Yeah.
this consistent with our findings. We need to find
But
the
even this value is about half of the value you actually see for the 80, right?
Mm.
80 was something like 28 or something like that.
Yeah.
The 80 potential energy.
Yeah.
So
But
if you,
for this one, the term actually better for this one.
Right.
So for the whole system,
right, I understand that.
the
It's interesting because you're saying that this is causing the mean flow to change.
Yeah.
to compensate this.
That's the whole point we're trying to explain. You saw the mean flow change. Remember that frontal picture, go back to the front picture again. This is the mean flow change. This is the control,
Mm.
Right.
and this is the filter, and that's the difference.
Yeah, that's.
You can see that in the control simulation, the mean flow is about 30% of maybe something like stronger.
Yeah.
And this is interesting because most of the classic ocean circulation theory doesn't tell us this at all. We assume the ocean circulation is entirely driven by the large scale forcing. But if this is really true, they're saying that the local feedback actually has a quite significant contribution to maintaining the mean ocean circulation too, which is kind of a really.
Well, unless the equations, that this is based on the model. The equations are consistent.
What do you mean by?
The equations they were using for this equation of motion, they describe the flow.
Yeah.
Those equations are true.
Well,
It has
those
to be a
equations
true
are-
effect, right?
Right, I mean, those equations I think pretty much should be true.
No, yeah, I mean, that's.
It's based on
story, right?
Newton's law.
No, what I mean is maybe there is some.
Right, I mean,
There
there
might
could
be
be
some small
numerical
curve.
issues,
Yeah.
yeah, but I don't think it's gonna be.
Well, the biggest uncertainty is maybe a harmonic mixing in the ocean.
Right.
That's all.
What I'm
Right,
saying
makes
is
sense.
a macroscopic equation. So unless there is some other terms that we don't.
There are parameterizations that some of the things are parameterized.
Well, in here, actually, we got rid of a lot of parameterization because resolution is so high. I mean, the coarse resolution model, for example, we have to use the Jan-McWilliams mixing to get 80 heat transport. Because we don't do the 80. But in here, since we're resolving the 80, so we actually don't even use the Jan-McWilliams, so we actually explicitly compute.
So the only thing is the vertical and horizontal diffusion.
That's right.
You can test the sensitivity.
Actually, the horizontal diffusion in this model is very, very weak. So it's, the only thing is actually the vertical, the KPPs, which could mess things up.
And the advection is really, when you say advection, it can be, it's not just horizontal.
Yeah,
It could be all.
but I have checked that the vertical direction is very weak because for the geotrophic flow, the vertical.
Should be zero, should be very
Very
weak.
weak.
Yeah. Okay,
So basically, this enhanced potential energy dissipation is compensated by the advection term. Not compensated by the conversion of the potential energy to kinetic energy.
although, but percentage-wise, it's still quite a large change though.
But this one, I will show you that this value is too small in the kinetic energy budget.
Okay.
So now find out the eddy kinetic energy budget. This is more complicated method.
Yeah, it's not
Potential
so
energy.
complicated.
So this is
Could you argue that when you turn off the feedback for the crucial, you go from a strong current regime to the
Right.
very active?
That's right. So you're gonna almost getting more meandering.
Could test that in the long run if they're more meandering.
Well, that's the problem. We could not
Mean
run the
state
model. Yeah, we couldn't. I mean, we haven't been able to run the regional model for very long. And that's the reason why we actually went to the ensemble approach.
Why can't you run it long?
Because energetically, we cannot say the regional model conserves the energy. When we come to
Drift.
the drift. And the global model is much easier to argue.
Once you drift, you can't tell it's because of the change in the mean state or because of the.
Exactly.
Both are.
Sorry, I have to, I'll be right back. You guys can go ahead.
So this is observing term and this is advection term. This is the barotropic instability term. And this is the conversion from the kinetic energy to potential energy. This is the pressure work. And this is the vertical dissipation term of eddy kinetic energy. This is horizontal dissipation term of eddy kinetic energy. So basically, we can see that in the control run, in the filter run, because we have a in the control run, we have a stronger eddy potential energy dissipation. So the conversion from the eddy potential energy to eddy kinetic energy is weaker in the control run. So in the filter run, it's some stronger. But this change of value is actually too small compared to other terms. We cannot find a dominant change in the eddy kinetic energy budget. So this should explain why we do not see a very significant change of eddy kinetic energy between the control run and filter run. So in the deep ocean, the change is not that significant between the control and filter run. So they are almost very similar. That's it. So this is the conclusions. So the thermal damping through the metascale LC interaction plays a key role in the eddy energy budget and is a dominant mechanism through which the eddy energy is dissipating. Note that, for example, you see this vertical dissipation in the kinetic sense, dissipation is about 7.6, but the dissipation is more than 2 times for the thermal dissipation. Another important conclusion that removing the thermal damping will lead to an evident increase of eddy potential energy and a significant weakening of the front and the mid flow.
Good. We're making progress, I think. This stuff is so hard.
So you can argue that the coarse resolution GCM are underestimating the strength of the front.
Yeah, definitely.
Because they don't have this
Because we don't have this anymore.
extra damping.
I mean, one thing, I think one implication of this thing really is that how we're going to run eddy resolving ocean model. Because we forced it with, actually, the concern is that now we're actually talking about a high resolution forcing field. So if you use a very high resolution rate analysis data, presumably it has imprint of the eddy already. Right? So you run this in, you run the high resolution ocean, and the ocean eddy generated in a different place than the imprint of the atmosphere forcing already.
Right.
So you're actually forcing the eddy in the wrong way, actually. Completely.
Yeah.
So that could be really a problem. I think it's actually better to not using high resolution products.
Filter out the
eddy effect, because you can actually mess things up even more. That's probably the worst way to do things. So that really is I mean, I
want to filter out the eddy effect, but you want to keep the small features, small scale.
Right. Somehow we have to either have some kind of a parameterization in the forcing field itself, so we can actually take into that consideration. Or you might just not considering that at all. But we don't know if we don't consider the eddy effects at all, this feedback at all, how much error we introduce into the ocean-only simulation. So that's the reason why in January, it's going to be a workshop in Japan. Because the next proposal, ocean community is going to use, they're going to get rid of the core forcing field. Core was based on NSAT rate analysis too, which has very coarse resolution, like 2.5 degrees. The next step is actually using the Japanese rate analysis data. JRA 55.
Oh, yeah.
So the question is that really the right thing to do or creating even more problems.
Well, solve some problem, create other problems.
Right.
Yeah, maximum.
So that's the discussion we're gonna have, and because the community, ocean community normally don't do the couple model simulation at all. I mean, they force the ocean model by itself. So the problem is that if the thermal damping is such a big energy source for the eddy, we eliminating that or we weaken that, then you force the ocean eddy to dissipate through the ocean mechanism. In other words, we could be over-tuning the ocean parameterization to force the ocean eddy goes away too.
Although in uncoupled run, there's a extra damping because you're doing the relaxation itself.
Right, that's right. Well,
That's not there in the coupled one.
right, so that's the thing, we need to do a comparison. We haven't done this, we've been talking about doing a comparison like that. You know, instead of doing the way we're doing it, we can actually just filter the surface variable, but still use the Watt formulation to compute the fluxes. That would be equivalent to use the low resolution atmosphere force in the ocean.
So that was my question. When we go to do like a coarse resolution forcing run and see how that compares to what you found.
We haven't done that yet.
Right.
That's the problem. We'll have to do that consistently. Because we have to change the way, right now, we actually, we don't use the Watt formulation to couple. We'll actually use the flux computed in the Wolf model directly. So if we want to do that way, we'll have to use
You can do
the
a,
Watt formulation in ROMs consistently.
no, you can use a coarse formulation.
No,
Do a
that's,
remap.
that would be, I think, we can discuss that. I think that's probably the same thing, but we can discuss
Well,
that.
at least you don't change the formulation.
But what we need to do is doing consistent. We have to rerun the coupled run.
Yeah.
And then run another filter run.
But I was thinking without filtering, just without filtering. Just do a coarse resolution atmosphere, which would be equivalent of removing the small scale. You're seeing it, I mean,
You can do that too,
Details.
but actually then the coarse resolution would have a different mean state as well. So it's more complicated.
Yeah, you can't.
You can't do that. So it's a much better doing the consistent way.
well, my point was if you can show that this is actually happening in the way people actually run stuff, because no one is running filtering. You know, we're trying to figure out what's going on, but people do run.
Well,
the ocean with a
I think
coarse
the better way to
resolution.
do that would be to use the Watt formulation consistent,
Yeah,
filtering
yeah.
the variables rather than the flux. Very good. Any other questions?
So we will expect similar thing in the downstream.
Should be. I think so. Probably all the ocean attributes. But that's why we're actually working with the NCAR teams, and one of the reasons Frank is here is actually we have to rerun the high-res. We got the 5 million allocations. We want to save all the diagnostic variables. We can do this energetic analysis. Right now, there's no way we can do anything because they don't save all those files. So yesterday, we spent a lot of time discussing that with Frank. And we can rerun those cases. That's the only way we can do it.
Yeah.
And then in that case, we can run the longer term, so we might be able to run the same steady state. By the way, if we check the longer term simulation of CSM, they have 11 years filter run. You see very similar things. For the things we can't compute, like entropy, you actually see a significant increase in entropy.
And you see the change in the front.
You
Yes,
change the front.
actually,
You
in
see
the
very consistent results.
in the CSM, the front is also weaker in the filter.
Yeah.
It's only the weak, or does it change in, does it move around?
It does change in CSM, actually going to the north. So
I think
this is
it's two different runs. So
Right.
Don't know. It's-
Okay. Because.
Right.
Mechanism.
The problem with the CSM is that on the global model, what we noticed that there's actually significant change in the tropics as well. So when the tropic change, then there's a remote inference in the crucial too, so you don't know whether this stuff is coming from local or it's coming from other source. Anyway,
The regional version of Sirius.
well, we were actually thinking about maybe filtering only locally. We could do that,
Yeah,
Yeah.
that's an option.
right? I mean, trying to keep the traffic, don't touch the traffic, just
Right, that might be a good idea.
maybe doing that instead of filtering the
Right, because
entire
it's a
road.
separate question. right?
Exactly.
Why,
Because when we look the filter wrong, I mean, the traffic changes is unbelievable. I mean,
you just put a transition zone and then
Right.
filter it.
Yeah,
That should be fine.
right. So that's the next week, we're gonna have some discussions about this, and how we will, if we rerun this, so we actually just filter the things locally. Instead of
That should be easy.
Yeah, it should be easy. No, that should be really easy.
It's the same mechanism.
The same mechanism. In fact, would it be a little bit faster because the filter going every block
Right.
point.
Yeah, I don't see any difficulty.
Right?
I don't know.
But
It's a little
anyway,
easy. Well, what the thing I see is, how are we gonna treat the interface? We need
it's a buffer zone.
We have to
transition
kind
zone.
of-
we need to define that.
Yeah.
YCC is.
Yeah.
It's
We
gonna-
have to do that.
I mean, but the thing is, you're still messing up locally, it's everywhere.
Yeah,
But that would be a very interesting spiral.
You might see even in that some topical influences.
Yeah, but it takes time.
You take
Yeah.
that.
For a year or two, it might be okay.
Right.
Yeah.
But anyway, we're gonna have some discussions next week with Stenka teams to see how we can do this together. Okay, very good. Thank you.
Thank you.
Have some cookies, guys. We need another box next to that.